Okay, we're going to look at a pre-lab that will kind of help us prepare for a lab coming up that has to do with stoichiometry and how we predict how much of a chemical we're going to make in a reaction. That can also help us evaluate how well our experiment went or if there are flaws in how we're running the experiment. Stoichiometry is just a fancy way of saying we're going to relate the amounts of chemicals to one another based on how they work in a chemical reaction. So this is going to be chemical reaction specific. It's not just something that works for, any relationship between any chemical. It depends on how they interact with each other. So in order to use that to our advantage, we're going to need a balanced chemical reaction equation. That's where we're going to start. So we're going to look at this reaction of magnesium and oxygen coming together to make MgO, magnesium oxide. In order to make sure this is balanced, I need to make sure that the number of atoms of Mg and O are the same as the number of Mg's and O's on the right side. So whatever I have over here has to also be over here. I can't have extras and I can't have stuff left out. So let's see, I have one magnesium on the left side of the arrow. I have one on the right, so that's good. I've got two O's in the reactants and one O in the product. That's not balanced. So how could I fix that? If I put a 2 here as my coefficient, that 2 is like a multiplier to say that I have 2 MgOs being made in this reaction. So I could apply that to everything in this chemical formula and multiply it through. So what that means is on the right in total, I have 2 Mg's and I have 2 O's. So now my O's match. I have 2 O's on the right. I have 2 O's on the left. But now my Mg's are a little messed up. I have 2 Mg's in the products and only 1 Mg in the reactants. So how do I fix that? Well, if I put a 2 here and say I'm starting with 2 Mg's, well, that only changes the Mg's. There's nothing else attached to it. So I have 2 Mg's on the left, 2 Mg's on the right. Hey, those match now. I still have 2 O's on the left and 2 O's on the right. So everything's balanced now. In total on the left side, I have 2 Mg's and 2 O's. In total on the right side, I have 2 Mg's and 2 O's. So in the end, I don't have to do anything with this. I'm just going to put a 1 there to make sure my math doesn't get messed up. So this is my balanced reaction equation. What this is saying is that 2 atoms of magnesium will react with 1 molecule of O2 to make 2 formula units or particles in general of MgO, of magnesium oxide. So in other words, 2 particles of Mg react with 1 particle of O2 to make 2 particles of MgO. Now, when we run a chemical reaction in the lab, we don't really see this happening atom by atom, molecule by molecule. We see it in bulk amounts. So dealing with this as, 2 particles of this and 1 particle of this is not really handy to us, especially if I want to measure out how much chemical I'm starting with and how much chemical I end up making. So instead, you might think of these as scaled up. I mean, as long as I have everything in the same kind of ratio of 2 to 1 to 2, it should still be balanced. So I could double everything and say 4 Mg's react with 2 O2s to make 4 MgOs, and that would still work. It might be a little excessive, but it's still balanced. So I could multiply everything through by 2, by 10, by 200, by a million, or by a mole. I could say that 2 moles of magnesium react with 1 mole of O2 to make 2 moles of MgO. And that still works. Okay, and that's going to be more convenient to us, and it's actually going to help us out a lot coming up here in this problem. So we'll see that in a second. But let's see this where we're at right now. Okay, so if we start with 2.00 grams of magnesium, we want to calculate how many moles of magnesium we're starting with. Okay, grams to moles. This is a conversion we've done before, so let's do it. 2.00 grams of Mg times a fraction bar. I don't want the unit of grams of magnesium anymore, so I'm going to want to get rid of it on the bottom of this fraction bar. So grams of Mg is going down here. Up on top, I'm going to want to have what I'm trying to convert to, which in this case is moles of magnesium. So I want moles of magnesium up here. Okay, so this is my conversion factor. So do I have a way I can go between grams and moles of something? Well, sure I do. This fraction bar, this relationship between grams of something and moles of something, is what we call the molar mass. And it's what we have on the periodic table at the bottom of every element. How many grams of that stuff are in 1 mole of that stuff? So for fraction bars like this, where we have grams and moles together, this is the molar mass in grams per mole. Okay, grams on one side of the fraction bar, moles on the other side. I just have to make sure I put the numbers in the right places. So to help with this, if we just have moles on one side of the fraction bar, we're going to be 1 with moles, which means we're just going to put a 1 next to the moles. 1 with moles. Okay, now this fraction bar is asking me how many grams of Mg are in 1 mole of Mg. Well, this is what the periodic table helps me with. So I'm going to switch over to the periodic table and find magnesium. Let's see, go up a little higher. All right, let's see, Mg. There it is. Okay, so this 24.31 down here is telling me that magnesium has a molar mass of 24.31 grams for every mole of stuff. So in 1 mole of magnesium, that should be 24.31 grams. Now, I don't actually have 24.31 grams of magnesium. I have 2. So my answer is not going to come out to be 1 mole. It's going to be a lot less. So when I do the math of this, my pen just died. Oh, nope, maybe it's just lagging. No, maybe it did die. Okay, let me put the battery back in. Okay, when I multiply by the top, I'm going to be tagging on my new unit of moles of magnesium. When I divide by the bottom, I'm going to be getting rid of my unit of grams of magnesium. So I should be left with moles of magnesium, which is what I want. Multiply by the top, divide by the bottom. So that's going to cancel out. So then I go and plug this into a calculator. 2.00 times 1 divided by 24.31 should come out to be about 0.082 moles of Mg. Okay, or something around there. It should be pretty close. Depending on your rounding, it might be a little bit different. But somewhere around 0.08 moles of Mg is what we're looking for. Okay, so that's not really super new. So that's good. It's a little familiar to us. Let's keep going. See what else we can figure out here. Maybe this lab won't be so bad. We react that many moles of Mg, what we just calculated, with oxygen in the reaction here. Calculate how many moles of MgO we will produce. Interesting. So we're going from moles of one chemical to moles of another. Well, I mean, usually if we wanted to figure out moles of MgO, we'd start with grams of MgO or particles of MgO and do a calculation kind of like what we did up here. But we don't have any of that information. The only information I have is about magnesium. So how do I figure out something about magnesium oxide, MgO, if my only information is based on a totally different chemical? Well, that's what the balanced reaction equation is going to help me with. Okay? Since this is telling me a ratio of how many particles of this and how many particles of that are going to react and form something else, this should also tell me the relationship between these guys that are needed for the reaction to happen. Not just at the scale of single particles, but at the scale of moles. I just scale them all up by moles. Well, if I look at what my reaction equation is telling me, when it's balanced, 2 moles of Mg of magnesium can be used to make 2 moles of MgO. That's what that's saying. 2 moles of Mg can be used to make 2 moles of MgO. O2 is included there too, but I'm just looking at the relationship between these two things for now. Okay, so I'm going to use this in a conversion factor to change from moles of Mg into moles of MgO. Okay, so we're starting out with what we know, what we're going to convert. Is 0.082 moles of Mg. Okay, I don't want the unit of moles of Mg anymore, so that's going to go on the bottom of this fraction bar. So I'm putting moles of Mg down here. Okay, what's the new unit I want? It's moles of MgO. Moles MgO. Okay, now, if I had moles on just one side of this fraction bar, like the top or just the bottom, then I could be 1 with moles. But if I've got moles on the top and bottom, it doesn't make a whole lot of sense for me to just be 1 with moles on both sides. Like, that would kind of defeat the point of making this a step in math. So we probably shouldn't do that. Yeah, this is going to be the only time you cannot be 1 with moles. Oh, and my pen just went out again. Okay, this is the only time we cannot be 1 with moles. So this conversion factor, moles of one thing to moles of another, has a special name. Let's see if that fixed it. There we go. All right, we call this a mole to mole ratio. Okay, and again, the numbers I put here are going to depend on the chemical reaction that they're related in. Okay, if it takes me 2 moles of Mg to make 2 moles of MgO, that's what I can put here. That's what this fraction bar is asking me for. What's the equivalent amount of moles of Mg and MgO? How do they affect each other in the reaction? So I'm just stealing these coefficients from here. So 2 moles of Mg, all right, are equivalent to 2 moles of MgO in this reaction. Okay, I didn't have to come up with any new numbers. I just stole them right from the equation I already balanced. Okay, so if we multiply by the top and divide by the bottom, our moles of Mg is going away. We're going to be left with moles of MgO. I take 0.082 times 2 divided by 2. What I get is 0.082 moles of MgO, which is going to seem wrong. You're going to be like, well, we got the same number. That can't be right. But it kind of will make some sense if we think of it like this. If we had exactly 2 moles of Mg, and we reacted it with oxygen, we should be able to make exactly 2 moles of MgO. Sure, they're going to have different masses, but the amount of moles, the amount of particles, is the same. So in this case, I don't have exactly 2 moles of Mg. I have 0.082 moles of Mg. So if 2 moles of Mg can make 2 moles of MgO, 0.082 moles of Mg should make 0.082 moles of MgO. Okay, now we still do the math and show this step because a lot of chemical reactions are not going to give you such an easy conversion here. It's not going to give you such an easy mole to mole ratio. Let me write that in here. Mole to mole ratio. Okay, sometimes it'll be a 1-to-2 ratio, or a 3-to-1, or a 3-to-4, or a 5-to-7. In which case, it becomes a lot harder to predict how many moles of this are going to make how many moles of that. And that's why we kind of do some number crunching with this, and we still write it as a conversion. Okay, but that's where the idea is coming from. It's all about the relationship in the balanced chemical reaction equation. There we go. Okay, let's see what's up next. If we produce that many moles of MgO, which is what we got here, calculate how many grams of MgO we'll produce. Okay, well, we got moles of MgO. Well, hey, we can go between moles and grams. We've done that before. We actually just did it up here, just kind of going the other way from grams to moles instead of moles to grams. So we're back in familiar territory again. Let's take this here and swing it down here. I want to convert my 0.082 moles of MgO into grams of MgO. All right, so we're going to start with what we know. which is 0.082 moles of MgO. All right. I don't want the moles of MgO unit anymore, so I'm getting rid of it. Doing a fraction bar. To get rid of it, my moles of MgO are going on the bottom. Up on the top, I want to try and figure out how many grams of MgO we're going to get. Grams of MgO. Okay, so I have a fraction bar to deal with here. Now, moles is only on one side of this, which means I can be 1 with moles. So wherever moles is in the fraction bar, I'm just going to put a 1 there. Okay, so now this fraction bar is asking me how many grams of MgO are in 1 mole of MgO. Well, that's asking for basically the molar mass. It's something we can get right off the periodic table. But instead of just grabbing the molar mass for Mg, we're also adding in an O to it. It's the molar mass of whatever is in our chemical formula for that substance. So I'm going to need to add up the molar mass of Mg and O to get the grams per mole of MgO, to get the molar mass. So before we said that the molar mass of just magnesium is 24.31, so we've got that part. 24.31 is our molar mass of magnesium, but we also need oxygen, so we're going to have to add something to that. So if we hop back to the periodic table, zoom out here. Hey, it's over there. All right, oxygen has a molar mass of 16.00. So let's add that in, 16.00. All right, so 24.31 plus 16.00 should come out to be about 40.31 grams of MgO in 1 mole of MgO. Okay, so there's our conversion factor. This will help us cancel out moles of MgO. It should get us to grams of MgO. And again, this single step is something we have done before, just like the first one was. There's nothing really new there. Okay, so if I take 0.082 times 40.31 divided by 1, and the divided by 1 doesn't really do anything to your math, but sometimes it's nice to do just to make sure you got everything you need. We should come out to about 3.305 grams of MgO. Grams of MgO. There we go. Okay, or again, something close to that. Maybe it's rounded to 3.31 or something like that. Okay. Well, does this answer make sense? If we had exactly 1 mole of MgO, then it would be 40.31 grams of MgO. But we don't. We have 0.082 moles, way less. So it's going to be way less than 40.31. So our answer is going in the right direction. So that's a good sign. Okay. Now, if we bring this all together, the implications of this are kind of crazy. Okay. What we started with was just grams of magnesium we're going to use in this reaction. Okay. And we're going to do this reaction in the lab. So if we take about 2 grams of magnesium, we go and burn it in oxygen, this is predicting that we should make about 3.305 grams of MgO out of this reaction. Okay, and I can figure that out before I even step foot in the lab, before I even get my magnesium, get my lighter ready. 2 grams of magnesium should be able to be used in this reaction to make 3.305 grams of magnesium oxide. Like, that's nuts. We can totally predict how much of something we're going to make, which is crazy. It just blows my mind. And it might not be super exciting to you right now, and maybe it won't ever be exciting to you, but it's exciting to me. We can use information about one chemical to figure out something about a totally different chemical, as long as they are involved in the same chemical reaction. Okay? It's crazy. And we're going to use this a lot. Okay? For instance, when we go and burn that magnesium and turn it into magnesium oxide, if we go and measure out how much we got and we get 0.5 grams, that's a lot less than we're expecting to get. So theoretically, we should have gotten this much. We're predicting we should get 3.305 grams of MgO. If we don't get that much, something's wrong with our experiment. We are losing stuff somewhere. Either it didn't burn completely, or we have something escaping from us. There's something going wrong. So we can use this to evaluate our experiments and make them better. and account for errors that might have happened along the way, because we are imperfect and we make mistakes. Also, sometimes it's hard to control what happens in a chemical reaction, so that also factors in as well. Okay, but that's the idea behind this. This is why we do this. It's not just so we can add another step to conversion factors and stuff. Stoichiometry helps us predict how a chemical reaction is going to go. And it can also help us predict just about anything, whether it's a reactant or a product. If I know I want to make 10 grams of MgO, I can use stoichiometry and convert to figure out how many grams of magnesium I should start with. Or if I want to know how many grams of oxygen are going to be used up in the reaction, well, measuring the amount of oxygen gas in the air in a big open room is very tough. And even if you have a sealed container, it can be very difficult. It takes a lot of equipment and care and stuff. So if I could just predict it based on how much magnesium I'm using and how much oxygen will have to react with it based on this ratio here, makes my life a lot easier. Okay? It's a great predictive tool in chemistry, and we're going to use it a lot through the rest of the semester. Okay, so this is going to be one part of our experiment, is burning magnesium in oxygen and seeing if we get something around the mass that we expect. Okay, we'll have something probably close to 2 grams, but maybe not exactly 2 grams. But let's look at the other part of this lab. Okay, we're going to be looking at baking soda. Okay, baking soda is also known as sodium bicarbonate, or just sodium hydrogen carbonate, as it makes it a little bit more sense. But this is kind of just the more traditional name. Okay, all three of those things mean the same thing. Sodium hydrogen carbonate, sodium bicarbonate is baking soda. In this reaction, we're just taking this sodium bicarbonate, or baking soda, and we're turning it into some other stuff. And there's 3 possibilities that could happen here. And the first possibility, our baking soda turns into sodium hydroxide and carbon dioxide. And the second possibility, our sodium bicarbonate turns into sodium oxide and carbon dioxide and water. And in the third possibility, our sodium bicarbonate breaks down into sodium carbonate, carbon dioxide, and water. Okay, in any of these 3 cases, we're just going to get this to break apart into these pieces by heating it up. We're going to take our baking soda and just put it over a Bunsen burner flame, get it so hot, we're going to cook some stuff out of it and cause it to decompose and break down. Okay, but what we make out of that is going to be a little bit difficult to determine. So out of these possibilities, we can make some balanced chemical reactions that are all viable and possible based on the elements we have in our sodium bicarbonate. We're going to see that here in a second. We also are going to have a hard time telling which one of these actually happens, because baking soda is a white powder, sodium hydroxide is a white powder, sodium oxide is a white powder, and sodium carbonate is a white powder. They all look the same. So we're not just going to be able to heat up the baking soda and be like, this one turned to green, so this is the reaction that's happening. We're going to have to be a little bit more clever than that to figure out which of these reactions is the real reaction that we see in the lab. Okay, and to figure that out, we're going to have to start with making some balanced chemical reaction equations. So let's start with this guy right here, our sodium bicarbonate breaking down into sodium oxide, carbon dioxide, and water. Okay, this is the one we're going to focus on right here. I guess I'll put a little star by it. Right there. Okay, so let's figure out some of the easier things first, since we have to write out the formulas for these guys ourselves. Well, water is a classic. Water is H2O. All right. Carbon dioxide tells us what's in it. And we've got 1 carbon, and di means 2, so that's 2 oxygens. So 1 carbon, 2 oxygens is carbon dioxide. The other 2 things are going to be a little bit trickier. Okay. Sodium bicarbonate and sodium oxide are both ionic compounds. We've got a metal bonded to either a polyatomic ion or a nonmetal. So let's start with our sodium bicarbonate, because it's going to be a little bit tricky if you don't know your polyatomic ions. Bicarbonate, if you don't know it, is HCO3 with a negative charge, which is why I tend to like to call it hydrogen carbonate instead, because it is basically the carbonate polyatomic ion with an H slapped onto it. And since the H has a positive 1 charge, it makes the carbonate have kind of less negative charge. It makes it a little bit more positive. So this is our bicarbonate or our hydrogen carbonate polyatomic ion. We're trying to get it to pair up with sodium. If you go find sodium on the periodic table, it's Na, and its charge, you have a shortcut up at the top of the column. Na, sodium, should have a charge of positive 1. Okay, Na, positive 1 there. I'm just gonna do a positive. Okay, well, those charges should cancel out. I should be able to take one Na plus and one HCO3 minus and put them together. My positive will cancel with my negative. I'll have no leftover charge. And that's a good sign that we've made the right chemical formula. Okay, this is the right chemical formula for sodium bicarbonate. So I'm going to stick those together. Put this down here. All right, so that's the formula for our sodium bicarbonate. So that's now also ready. The last thing we need to figure out before we can balance this reaction is the correct formula for sodium oxide. Okay, so we said Na has a positive 1 charge. In this case, we're trying to bond it to oxygen. That's right, O for oxygen here. Let's go figure out what kind of charge oxygen is going to have. Swing this over here. Oxygen should have a negative 2 charge. All right, so get a little negative 2 charge up there. So if I put together just one Na and one O, those charges aren't going to cancel completely. We're going to have a leftover negative charge. So one Na with a 1 positive charge is not going to be enough. I would need 2 of them. If I had 2 Nas, that would be a positive and a positive. A positive 1 and a positive 1 should cancel with a negative 2 charge. So that's what we're going to do. We're going to cancel those out. And this should be the formula that I'm using for sodium oxide, Na2O. Okay, now that I've got all my chemical formulas, I'm ready to balance. The one thing I want to avoid doing first is oxygen, because oxygen is in so many places. It's in my bicarbonate, my sodium bicarbonate, it's in my sodium oxide, it's in my carbon dioxide, it's in my water. If I try and balance the oxygens first, I'm going to be stuck forever just going back and forth trying to get these to work out. So instead, let's start with some of the elements that just show up kind of in one place on each side. So like our sodium. So I have 1 sodium on the left side. I have 2 sodiums on the right side of the arrow. So if I want 2 sodiums on the left to match the 2 on the right, I'm going to need a coefficient of 2 here. Okay, so that way I've got 2 Nas on the left to match the 2 Nas on the right. Now, this also affects the rest of the formula. I can't just pick and choose. So I have 2 Nas. I also have 2 H's, 2 C's, and twice as many oxygens here. So if I already had 3 O's, now I have twice that. That's going to be 6 O's. Okay, so that's going to affect kind of the rest of my balancing from here on out. So since I have 2 sodium bicarbonates, that's 2 Nas, H's, and C's, and 6 O's. Okay, so my sodiums are balanced. Let's look at our H's next, our hydrogens. Well, I have 2 H's on the left, and hey, there's already 2 H's on the right, so those are good. So I can leave that alone. That doesn't need to be balanced. Let's see, what about C? What about carbon? Well, I have 2 C's on the left side. I only have 1 on the right side, so I should probably fix that. So if I put a 2 right here, okay, 2 CO2s means I'm going to have 2 C's. It also means I'm going to have twice as many O's. But we haven't balanced the O's yet, so we're not really missing out on much here. So that's okay. Okay. So we did the NAs, we did the H's, we did the C's. So all that's left is our O's. Well, on the left side, we had 6 O's, because it's 2 times 3. On the right side, in total, we have 1 O here. We have 2 times the 2 O's here. That's 4 O's. Okay, and I have 1 O here. So in total, I have 1 plus 4 plus 1. That's a total of 6 oxygens. Hey, and we had 6 over on the left side too. So those are already balanced as well. So I could just put 1 there and 1 there because everything's already balanced. I'm just going to fill in the blanks with 1s. And this is going to be my balanced reaction equation. Okay. Now, to kind of put emphasis on why we needed to get the correct formula here, all right, our Na2O affects the balancing based on how many NAs and O's there are in this formula. Okay, if there is just one Na and one O, and I didn't try and fix the kind of charges that weren't canceling, I'd end up balancing differently. And we saw from the example above that we end up using these numbers in our conversion factors to go from moles of one thing to moles of another. So that's going to make our lives a lot harder if now our balancing is wrong or something like that. We're going to end up making a mistake somewhere. So we got to be careful about our formulas. We got to make sure the charges cancel. And that's why we took so much time on it to kind of work on canceling charges, getting the right formulas, whether it's ionic or covalent. Okay, so we now have a balanced reaction equation. So next up, we're going to be looking at how we can use stoichiometry to predict how much sodium oxide we should get out of a certain amount of sodium bicarbonate. So let's look here. Okay, if we start with 2.00 grams of sodium bicarbonate, we're going to try and use stoichiometry to figure out how many grams of sodium hydroxide we should make, how many grams of sodium oxide we should make, and how many grams of sodium carbonate we should make. So these are basically the three possibilities of the stuff we could make from these reactions, either sodium hydroxide, sodium oxide, or sodium carbonate. Since we just did the sodium oxide reaction equation, we'll probably roll along with that. Also, just to kind of save some effort, you're looking at, seeing like, oh, I've got like 3 more of these to do, or 2 more of these to do. That can be a little daunting, but remember, some of this is going to repeat. So like, it's also carbon dioxide right here. That's CO2. Hey, there's carbon dioxide right there. That's CO2. Okay, there's water again, H2O. Okay, and in each of these cases, we're starting with the same step. We're starting with sodium bicarbonate, which we said was NaHCO3. NaHCO3. So really, for the other two reactions, you just have to figure out what sodium hydroxide is, what sodium carbonate is, and then balance those reactions. So hopefully that saves you a little bit of work. Use what you already figured out. Don't reinvent the wheel every time. Okay, so if we start with 2.00 grams of sodium bicarbonate, we want to figure out how many grams of sodium oxide we should make out of the reaction. Okay, so we are using this reaction equation up here. Again, the one that we figured out already. And I want to try and figure out, I'm going to say, we know we have 2.00, ooh, that was a little bad, 2.00 grams of NaHCO3, and we want to figure out how many grams of Na2O we're going to make out of that. Let's do a different color. Question mark grams. How many grams of this? So we want to use stoichiometry and unit conversions to get from grams of this to grams of this. Now, I wish we could just go from grams of this to grams of this, but we don't have a unit conversion for that. We don't have a conversion from grams of one chemical to grams of another that just goes straight from one to the other. Now, trying to keep track of conversions like this can be very hard when we don't have it kind of broken down like what we had up here. From here, it told us, go from this to this, go from this to this, go from this to this, and we could just kind of walk through our fraction bars like that. But in this case, it just says go from grams of one thing to grams of another. So, like, where do we even start, and how do we know we're not doing something like math illegal when we do our conversions? Well, that's what the stoichiometry diagram is for. So let's flip to this. I'm going to zoom out a little bit and go down to our stoichiometry island diagram. Okay, so on this diagram, each island is a unit, like grams of a chemical or moles of a chemical or particles of a chemical. We're not going to need this volume stuff right here and right here. So actually, let's get rid of it. So I'm just going to kind of wipe this out of the way for now so we can ignore it. Also give us a little bit more room. Okay, so we are starting with grams of sodium bicarbonate. We're starting with specifically 2.00 grams of NaHCO3. Okay, well, if I am going to convert, again, it would be great if I could just go straight from NaHCO3 and grams to grams of something else. Just hop from mass of one thing to mass of another. After all, we're trying to get to grams of a different chemical. In this case, grams of sodium oxide, Na2O. Okay, but if I don't have that conversion factor to go magically from grams of one thing to grams of another, that's where we need to kind of follow these islands. It's where we're going to kind of go from bubble to bubble to bubble, and each one is a conversion. Okay, so I can't go straight from grams of one thing to grams of another, but I can go from grams of one thing to moles of that thing. And that's going to be our first step, okay, on our path to solving this problem. I'm going to change from grams of NaHCO3 into moles of NaHCO3. Moles NaHCO3. Okay. From there, if I'm still working on my path to get to grams of Na2O, the only place I can go that makes sense is go into moles of a different chemical. Okay. That new chemical is going to be Na2O. Moles of Na2O. Okay, so that's going to be another conversion from moles of one thing to moles of another. Okay, my last conversion is going to be going from moles of Na2O, finally, to grams of Na2O. All right, we've done these conversions before. It's just tougher to kind of chart out if you don't have the diagram with you to kind of say, oh, I can go from this to this, and this to this, and this to this. Okay, so this is the path we want to try and take. We want to try and go from grams of NaHCO3 to moles of NaHCO3. We want to try and go from moles of NaHCO3 to moles of Na2O, and then from moles of Na2O to grams of Na2O. Now, we're also not going to stop at every point in between and get an answer because we really don't need that. All we want to know is grams of Na2O. I don't need to know how many moles of NaHCO3 we're going to have or moles of Na2O. So we're just going to basically stick fraction bars together until we can convert our units to the thing that we want, starting with this 2.00 grams of NaHCO3. Okay? If we're going between grams and moles, don't forget, oh no, where'd my red go? I have to go grab the red again. Now let's see, which red do I want? All these look like different reds. Maybe it was this one. I'll go with that. Oops, I'm still on blue. Yeah, it might be a little bit different, but it's close enough. Okay, so if I'm going between grams and moles, don't forget that we're going to be one with moles. Okay, and 1 mole of something is equal to the molar mass of that stuff in grams. Okay, same thing if we're going from moles to grams over here. We're going to be 1 with moles and use that molar mass from the periodic table. Okay, let's make a note of that over here. Molar mass on periodic table. Okay, whether we're going from grams to moles or moles to grams, we're going to be 1 with moles and use the mass from the periodic table, add it up on the gram side of it. Okay, if we're going from moles to moles, that's our fabled mole-to-mole ratio, where we're using the coefficients from our balanced chemical reaction equation to go from one thing to another. So when it says substance A, it means the chemical we're starting with. So our substance A is NaHCO3. Substance B is the stuff we're trying to convert into. So that would be our Na2O in this case, or sodium oxide. Okay, so this is our mole-to-mole ratio. Okay, and this is the only time we cannot be 1 with moles. Only time we can't be 1 with moles. Okay, we're using the numbers for the coefficients from our balanced reaction equation. Okay, so let's try and work this out using this chart we've kind of, or this path we've charted out, or we've charted out our course or something, to hop from island to island here, from bubble to bubble. So we're going to start with going from grams of NaHCO3 to moles of NaHCO3. And we're going to let this guide us and show us what units we need to change to. Okay, so we're starting with 2.00 grams of NaHCO3, and we were just given that up here, starting with 2.00 grams of sodium bicarbonate. My first conversion is going to get rid of grams of NaHCO3, and the unit I'm going to be hopping to is going to be moles of NaHCO3. Moles is kind of like our ultimate converter, or universal converter between stuff. So it's great to get to moles if you don't know where to go. Okay, so moles is just on one side of this fraction bar. It's not a mole to mole ratio, so I'm going to be 1 with moles. So this fraction bar is asking me how many grams of NaHCO3 are in 1 mole of NaHCO3. So I'm going to need to add this up from the periodic table. So I'm going to have, I'm just going to do it kind of up here so it's out of the way. I have 1 Na, so 1 times my Na's molar mass, plus I have 1 H, 1 times my H's molar mass, plus I have 1 C, so 1 times my carbon's molar mass, plus, and I have 3 oxygen, so 3 times my O's molar mass. It's not a 0, that's an O. Okay, so if I go check the periodic table and get these molar masses, oh, come on, there we go. Scrolling up here. Sodium is 22.99. Hydrogen is 1.01. Carbon is 12.01. And oxygen is 16.00. So let's throw those in. Sodium was 22.99. Hydrogen was 1.01. Carbon was 12.01. And oxygen was 16.00. Okay, so let's add all that up. So 22.99 plus 1.01 plus 12.01. All of this here, since it's all just 1 times this stuff, is going to be about 36. Oh, wow. Come on. Here we go. 36.01. Right there. Okay. Plus 3 times my 16 right here. Okay. So 3 times 16 is 48. Okay, so 36.01 plus 48 gets me 84.01. Okay, that's how many grams, 84.01, how many grams of sodium bicarbonate are in 1 mole of sodium bicarbonate. So this should allow me to cancel out my grams of NaHCO3. All right, now I've got a unit of moles of NaHCO3, so I can look at what bubble I'm going to hop to next. So we got out of grams of NaHCO3. We are on to moles of NaHCO3. We are now here. So the next step is to go from moles of NaHCO3 to moles of Na2O. It's our mole to mole ratio. Out of the way. Okay. So I'm going to multiply by a fraction bar. Where I want to get rid of moles of NaHCO3 on the bottom. Moles NaHCO3. Right? And on the top here, I'm looking at getting moles of a different chemical, of sodium oxide. So moles of Na2O is going up here. Okay, so I'm not just going to be one with moles. If I've got a mole to mole ratio like this is where I need to go to my balanced equation to figure out how many NaHCO3s can make how many Na2Os. So let's go check that. So on the equation we balanced up here, ooh, my whole page went away. That's okay, we've got the balanced equation. Okay, 2 NaHCO3s should be able to be used to make 1 Na2O. So for my mole to mole ratio, 2 moles of NaHCO3 can be used to make 1 mole of Na2O. All right, and that's what my balanced equation tells me. So my moles of NaHCO3 should cancel out. Those are gone. All right, I now have moles of Na2O. So where can I go next? Got rid of, moles of NaHCO3. I'm now here at moles of Na2O. My last step is to get to grams of Na2O. So I just need one more fraction bar left to change from moles to grams. So finally, set up my conversion factor there. I want to get rid of moles of Na2O on the bottom here. Moles Na2O. Okay. On the top, I'm trying to convert to grams of Na2O. All right. This is not a mole to mole ratio, so I can be 1 with moles. I'm going to put a 1 down here. All right. So this question is asking me, in 1 mole of Na2O, how many grams of Na2O do I have? So I'm adding up the molar mass of 2 NAs and 1 O, just like I did up here for my NaHCO3. So each Na was 22.99, so this is going to be 2 times 22.99 plus my 1 oxygen, which is 16.00. Since 1 times 16.00 is just 16.00, I'm just going to write that. So 2 times my 22.99 gets me 45.98 plus 16 is going to give me 61.98. 61.98 grams of Na2O in every mole of Na2O. All right, so my moles of Na2O are going to cancel out here. I'm going to be left with grams of Na2O, which is what we're trying to figure out in grams of sodium oxide. Okay, so now all I have to do is calculate this. So I'm going to be multiplying by the top, dividing by the bottom. You can ignore the ones or you can include them because they won't change your math, but sometimes it's nice to keep tabs on everything that's in here. So I'm going to take 2 times 1 divided by 84.01 times 1 divided by 2 times 61.98 divided by 1. What I get is 0.738-ish grams of Na2O. And that is my answer. So how does that help me? Well, I know if the reaction that happens when I cook the sodium bicarbonate, when I heat up my baking soda, if it breaks down into 0.738 grams of Na2O, that's a good sign that I've made sodium oxide. Okay? If it broke down into something like sodium carbonate or sodium hydroxide, I'd end up with a different number of grams of that stuff. Okay, and that's what we're going to be doing the stoichiometry up here and down here for. Okay, so if I start with 2 grams of NaHCO3, I should get 0.738 grams of Na2O if this is the reaction that happens. Okay, if it's not, then I'm going to get some other amount. Okay, so hopefully that has been helpful. The other two are going to be similar to this, and we're starting the same way. We're still going to start at grams of sodium bicarbonate, okay, specifically 2.00 grams of it. And then we're just figuring out something else, either grams of sodium carbonate or grams of sodium hydroxide. So make sure you finish the reaction equations up here that are now like blanked out for some reason. Make sure you finish those. Make sure you get them balanced, and then use that stoichiometry diagram to help you through. It should be pretty similar to this, and you might even see that a good chunk of the beginning of it is going to be pretty much the same as the way we started, since we're trying to convert out of grams of NaHCO3, trying to get to grams of something else.